In the previous lecture, we defined climate. We describe here the notions of heat and temperature. These notions, along with electromagnetic waves and electromagnetic spectrum that we will discuss in the next lecture, are central to the understanding of climate change from a geophysics perspective. Remember that global warming essentially refers to heat. That is why this lecture focuses on developing our understanding of the notion of heat and on how heat moves around. Your learning objectives are to understand the differences between diatomic molecules and polyatomic molecules. Understand the difference between heat and temperature. Familiarize yourself with the concept of molecule vibration. Familiarize yourself with the conduction, convection, latent heat, and radiation. These notions describe how we move the heat around. Familiarize yourself with the 3 temperature scales: Celsius, Fahrenheit, and Kelvin. Also familiarize yourself with the notion of absolute zero temperature. Heat is the measure of the motions of atoms, which compose the matter whose temperature we are trying to measure. Therefore, it is important to start by introducing atoms and molecules and their motions. We'll start with atoms. The atom is a basic unit of matter that consists of a dense central nucleus surrounded by a cloud of negatively charged electrons. The atomic nucleus contains a mix of protons and neutrons. Protons are positively charged particles located in the nucleus. Neutrons are neutrally charged particles located in the nucleus. Electrons are negatively charged particles which revolve around the nucleus. An atom is classified according to the number of protons and neutrons in its nucleus. The number of protons determines the chemical element, and the number of neutrons determines its isotope. Let me repeat this. An atom is classified according to the number of protons and neutrons in its nucleus. The number of protons determines the chemical element, and the number of neutrons determines its isotope. The atomic number, also known as proton number, is the number of protons. The atomic weight is the number of protons plus the number of neutrons. A molecule can be composed of one or several hundreds of atoms. A molecule may consist of the atoms of a single chemical element, such as oxygen or O2, or of different elements, such as water or H2O, methane or CH4, and carbon dioxide or CO2. Here are examples of 1 atom, 2 atom, 3 atom, and 5 atom molecules. All matter is made up of atoms and molecules that are constantly moving. Yes, although we do not see them with our naked eye, atoms and molecules are constantly moving in a given matter. Molecules interact with one another through electric forces. These forces allow individual molecules to move, but they still confine liquids and solids to a specific volume. Let's talk about restoring forces. Any given molecule will feel many forces, some that attract and some that repulse. A restoring force is a net force that always restores the molecule to some central position. Springs are used to describe restoring forces. A spring is an artificial construct used in the context of thermal energy. If two molecules are pushed toward one another, the spring connecting them is compressed. The spring pushes back, trying to restore the molecules to their original separation. If two molecules are pulled apart, the spring again resists the force, this time pulling back toward one another. Springs here are used to picture how electrical forces allow individual molecules to move, but they still confine solids, liquids, and gases to a specific volume. The molecules of a solid are held together by strong restoring forces. Liquid molecules do not experience as strong a restoring force as a solid. The weakest restoring forces are those of gases. Let's now talk about molecular vibration and heat. A molecule with two or more atoms is held together by strong chemical bonds. An atom can participate in more than one chemical bond. The bonds arrange themselves around the atom to find their positions and the angles of least energy. There is some flexibility in the angle of the bond, which leads to bending vibrations. That is, vibrations which involve changes in the angle between two bonds. The notion of bending vibrations is very important in regard to climate change studies. A molecule can vibrate and move, depending on the number of atoms from which it is built. These bonds continually vibrate and move. They can vibrate with stretching motions or bending motions. Let's watch some 2-atom and 3-atom molecules in motion. These molecules are nitrogen, oxygen, and carbon dioxide. The 2-atom molecule, also known as diatomic molecules, can move in 3 ways. The entire molecule can move back and forth in a straight line as a 1-atom molecule. The 2-atom molecule can remain in a fixed location while its atoms rotate or vibrate about its center. Basically, a 2-atom molecule can move linearly, that is, through translation, rotate, and vibrate. Again, the 2-atom molecule, also known as diatomic molecules, can move in 3 ways. The entire molecule can move back and forth in a straight line, that is, the movement of each atom toward or away from the other atom. The 2-atom molecule can remain in a fixed location while its atoms rotate or vibrate around its center. Basically, a two-atom molecule can move linearly, rotate, and vibrate. Let's watch more 3-atom and 5-atom molecules, which are water and methane, in motion. The 3-atom molecule has even more possibilities. Actually, complex molecules can do it all: move linearly or through translation, rotate, and vibrate all simultaneously. Water and methane molecules, for example, can rotate and vibrate in a number of ways. Substances with high specific heat capacities consist of complex molecules that can vibrate and rotate in a variety of ways. A polyatomic molecule is a single entity composed of at least 3 covalently bonded atoms, for example, H2O and CO2. Note that the linear motions include symmetric and asymmetric stretching. Here is symmetric stretching. Here is an illustration of asymmetric stretching. Again, complex molecules can move linearly, rotate, and vibrate all simultaneously, including bending vibrations and vibrational modes where the angle between atoms change. Here are illustrations of bending vibrations of carbon dioxide, for example. Substances with high specific heat capacities consist of complex molecules that can vibrate and rotate in a variety of ways. When heat is added to matter, that is, a substance, the molecules and atoms vibrate faster. As atoms vibrate faster, the space between them increases. The motion and spacing of the particles determine the state of the matter of the substance. The result of increased molecular motion is that the object expands and takes up more space, but the mass of the object remains the same. Solids, liquids, and gases all expand when heat is added. When heat leaves all substances, the molecules vibrate more slowly. The atoms can get closer to each other, and the matter contracts. Again, the mass is not changed. Here is an illustration of solid expansion with heat. Again, when heat is added to matter, the molecules and atoms vibrate faster. As atoms vibrate faster, the space between atoms increases, but the mass of the object remains the same. However, as the numbers of atoms in molecules are unchanged. Here is an illustration of liquid expansion with heat. When heat leaves all substances, the molecules vibrate slower. The atoms can get closer, which results in the matter contracting. Again, the mass is not changed. The kind of heat in a given matter depends on the atom motion in the matter. Again, atoms can move as translation, vibration, and rotation. The vibration atoms in gases and liquids is a very important notion for greenhouse effects that we will describe later. Each mode of motion stores an energy that is proportional to the temperature. Another important result here is that the temperature is directly related to heat, but temperature is not the same thing as heat, although the two words are often used interchangeably. We will revisit this issue later. How do we move the heat around? That is the question we will try to answer in this section. Energy moves in the climate system from one form to another. Therefore, it is important to recall how thermal energy, or heat, can move from one place to another. Heat can move in 4 ways: through conduction, convection, latent heat, and radiation. Let me repeat this. Heat can move in 4 ways: through conduction, convection, latent heat, and radiation. Let's review these 4 ways. We will start with conduction. Heat energy is most intense in substances whose molecules are moving rapidly in a very disorderly way. Such substances will give up some of their heat to another substance whose molecules are less agitated. When this happens, the heat is said to flow from one substance to another, or from one body to another. The energy transfer is indicated by a change in temperature. This transfer of heat is known as conduction, which requires the presence of matter and therefore can occur only in solids, liquids, and gases. So conduction is a good way of moving heat around when dealing with objects, such as solids, liquids, and gases, in contact with each other. But it is not useful in a vacuum, that is, regions where there is no matter, such as space. In other words, conduction is not important for heat exchange between the Sun and Earth, or for climate sciences, because there is nothing to conduct heat through between Earth and space. Let's talk about another way of moving heat around, which is through convection. Thermal energy can be transferred from hot places to cold places by convection. Convection occurs when warmer areas of a liquid or gas rise to cooler areas in liquid or gaseous form. The cooler liquid or gas then takes the place of the warmer areas, which have risen. This exchange results in a continuous circulation pattern known as convection. Water boiling in a pan is a good example of convection currents. Convection is important for describing the motion of the atmosphere and ocean on both local and global scales. Let's talk about another way of moving heat around, which is latent heat. When a substance changes phase, changing from a solid to a liquid or a liquid to a gas, it requires latent heat energy to do so. For example, heat is needed to transform water to vapor. This way of moving heat is used in the climate sciences in relationship with the water cycle between the oceans and the atmosphere, as we described in a previous lecture in the context of water cycle. Finally, let's talk about radiation, which is another way of moving heat around. Radiation is a method of heat transfer that does not rely upon any contact between the heat source and the heated object, as is the case with conduction and convection. Heat can be transmitted through empty space by thermal radiation, often called infrared radiation. Radiation absorption is accomplished directly through electromagnetic interactions. The process involves the motion of atoms and molecules at the beginning, radiation, and the end, absorption, of the process, but not during the actual transfer through space. Basically, the thermal energy present in the vibrations of the molecules in the energy source is transferred to the thermal energy in the vibrations of molecules in the energy receiver. Electrical forces are responsible for the entire process. The energy travels through space in the form of electromagnetic waves. Examples of radiation include the heat from the sun. Energy can travel through empty space from the sun to the Earth and other planets in the solar system. Radiation also occurs within the climate system, between the Earth's surface and the atmosphere, and within the atmosphere and the ocean. Radiation is important and even central to climate science studies. In summary, all forms of heat transfer move heat from one body to another, or from one part of a system, such as the climate system, to another. Heat always moves from a place where the temperature is relatively high to a place where it is relatively low. Let me repeat this. All forms of heat transfer move heat from one body to another, or from one part of a system, such as the climate system, to another. Heat always moves from a place where the temperature is relatively high to a place where it is relatively low. Let's conclude this lecture on heat by talking about temperatures. Again, the amount that molecules are vibrating, rotating, or moving is a direct function of the heat content. Heat is energy. Let me repeat that. The amount that molecules are vibrating, rotating, or moving is a direct function of the heat content. Heat is energy. It is the total amount of energy possessed by the molecules in a piece of matter. Temperature is not energy. Let me repeat this. Temperature is not energy. Temperature is the measure of the average molecular motions in a system. Let me repeat this. Temperature is the measure of the average molecular motions in a system. As heat energy increases, the temperature will also increase. So, temperature is not the same thing as heat. Temperature can be defined as the degree of intensity of hotness or coldness. A hot body becomes cooler, and a cold body becomes warmer, as long as heat is flowing from one to the other. The hot body has a greater ability to give up heat, and therefore has a higher temperature. There are 3 temperature scales: Celsius, Fahrenheit, and Kelvin. Temperature scales differ in 2 ways. The point chosen is 0 degrees, and the magnitudes of incremental units or degrees on the scale. The Celsius scale or degrees Celsius, is used for common temperature measurements in the world. Its 0.0 degrees Celsius is defined as the freezing point of water, with additional degrees defined so that 100 degrees Celsius was the boiling point of water, both at sea level atmospheric pressure. The United States commonly uses the Fahrenheit scale, on which water freezes at 32 degrees Fahrenheit and boils at 212 degrees Fahrenheit at sea level atmospheric pressure. Scientists generally use the Kelvin temperature scale, that is, the unit symbol K, because it preserves temperature information even when dealing with temperature at even power. Its 0 degrees Kelvin is defined to coincide with coldest physically possible temperature, called absolute zero. The temperature of absolute zero occurs at 0 degrees Kelvin, or minus 273 degrees Celsius, or minus 459 degrees Fahrenheit. And the freezing point of water at sea level atmospheric pressure occurs at 273 degrees Kelvin, or 0 degrees Celsius. Here is a useful table for moving from one temperature scale to another. In the first equation, we move from the Celsius scale to the Kelvin scale. In the second equation, we move from the Celsius scale to the Fahrenheit scale. In the third equation, we move from the Kelvin scale to the Fahrenheit scale. Here is another table for moving from one temperature scale to another. Remember, there is a large selection of iMode education lectures, which can further enhance your knowledge of earthquakes, volcanoes, climate, and energy. Thank you for listening to this iMode education lecture.